So, hello to all our respected judges. Today, me and my team will present our satellite mission, the Radiation Belt Ionosphere Observer. So first, we'll start with the mission objectives. So our main purpose of our mission is to collect data relating to both radiation belt dynamics and ionosphere dynamics, so we can map out regional and global models, hopefully to understand the dynamics better and increase the accuracy of these models too. So on top of that, our mission also will help to bridge the gap between high cost data rich satellite missions like the radiation belt probes and the low cost, lower accuracy data set CubeSat missions such as the RPT TAR CubeSat mission, and by trying to compromise between both of them by providing a medium cost but data rich satellite mission, which we're presenting today. So next, I'll pass it on to my colleague Yinjia to present the stages of the mission.
Greeting to all the judges. In the stage 1 of our mission, the rocket will firstly go into this height and release our satellites, and the satellites will maneuver in this low Earth orbit until it reaches the design position. And in stage 2, the propulsion system will produce a sudden acceleration at the design position and move the satellite into an elliptical orbit, which is called the inner belt. And the satellites will complete the mission in the inner belt through this orbit. And in the stage 3, the satellites will accelerate again and enter a circular orbit. This circular orbit is used for transferring to the next orbit. And in the stage 4, it's the satellites maneuver from the previous orbit into the next elliptical orbit, and it's called the outer belt orbit. And this orbit is used for the mission in the outer belt. And this is the orbit model by the GMAT with the ground track by the GMAT. And in the end of our mission, we are going to destroy our satellites by propulse it towards the Earth when it is at the nearest point to Earth. And after the satellites enter the Earth, it will destroy eventually by the ionosphere. So then is the collision prevention system. Our collision prevention system works with different kind of data sources. Firstly, the data sources will track with our satellites and the debris around it. If there is any dangers or debris near to our satellites, the data source will automatically design an avoiding routine for our satellites. So our satellites will move into the avoiding orbit and stay in the orbit until the danger is removed. Then the satellites will move back to the original orbit and continue its mission. So now I give the time to my other teammates to talk about the other parts of the mission.
So we will now talk about instrumentation. So this is a list of the instrumentation we will use in our satellite. Firstly is the electric fields and waves, cluster spin plane boom, and then the mag, which is a magnetometer. Next is the low energy particle experiments, which is an electron analyzer. Next up is the extreme high energy electron experiments. And then next is the HEP-C, Pluto energetic particles spectrometer science investigation. And the next one is the RP-TAR, which is the relativistic, the miniaturized version of the relativistic electron proton telescope. And lastly, the RB-SPICE. The RB-SPICE is the radiation belt storm probes ion composition experiment. So this is the data flow chart of a simple data flow chart of the data we'll be using for this mission. So as you can see, firstly, our instrumentation will go into a modeling system, and the local and global modeling system will go to our database for eventual analysis. So there are two ways that we will get our ionosphere model. For the local ionosphere model, we'll be using incoherent scatter radar modeling. More specifically, we will use the we will use this to model the ionosphere for the local model. And then the next one would be the global modeling, which will be done by GPS tech or total electron content by the IDA 3D model of the ionosphere to get a global modeling of the ionosphere and its electron density. Next up, we will from the collection of our data in the satellite mission, we will use to model uh, the I mean the we will use it live, sorry, to model the comprehensive inner magnetosphere ionosphere model of the radiation belts. As you can see here, this will give us an update, a live update on the dynamics of the radiation belts. So the question is really, why would we use models? So while researching about the radiation belts, I stumbled upon modeling and how many numerical models and machine learning models people have been scientists have been researchers have been working on these days to model the dynamics of the radiation belts. So we thought we would pitch in and help this out. So expanding on the reason why we chose models, because we want to expand and improve the nonlinear wave particle interactions modeling, which is still a fuzzy field and not truly understand with modeling yet. So the interactions between IC wave packets and electrons driving electron precipitation. And we also want to help increase the CIMI modeling in solar storm conditions, because results have been a bit weak during these situations, so we want to help out. And for looking even more in the future, right? The onslaught of new predictive models, new machine learning predictive models, we want to collect data to help that building of those models. Same here for the ionosphere. Not really same here, so we will add some extra stuff for the ionosphere. So we want to observe the changes in the atmospheric electroconductivity, mostly just the changes in the dynamics actually in the ionosphere due to maybe due to electron precipitation through and from the radiation belts. So and also contribute to building predictive models. And I'll move on. I give my time to my colleague Winnie.
Hi, I'm Winnie, and here's our satellite design for a propulsion system, energy storage and distribution system, communications, control system, and lastly, radiation protection. Yep, that's all. Thank you.
Thank you. Thank you for your time.